Okay, by definition, it's the definition of an inverse says pretty much this. If you're trying to show that two functions really are inverse functions of each other, then you have to evaluate these compositions where you plug G into F, and then you have to turn around and plug F into G. And the result of plugging G into F means that your equation is going to reduce down to X. And the same thing is going to be true over here. When you plug the F function into the G function, it's also going to reduce down to X. So we have to do function composition in order to show or prove that two functions are inverses of each other. All right. So I have an example worked here. So the first function that we're going to do, I kind of left this off. So I want to show that those two functions that I worked with over there really are functions of each other. So the f function was f of x equals 2x minus 3. And then I found the inverse of that was x plus 3 over 2. Now, it will work with this notation that I'm using right here. I'm also going to rename this function. It didn't come out to look very much like the inverse function. I'm going to call the inverse function g of x. That way it'll fit this. So the f function says that if we're going to take and prove that it's equal to x, we're going to take the f function and we're going to plug the g function in everywhere we see an x value. So the x function right here, the g function is x plus 3. So this is the g function. I'm plugging it into the f function. Here's the g function. I'm plugging it into the f function right here. I do x plus 3 over 2. All right, so if I am plugging that in, let me move this over a little bit. I still want to hide that one. So if I plug that function in and then I distribute the 2, well, the 2's are going to cross out. And because if you multiply by 2 and then you divide by 2, well, multiplying and dividing by 2, they undo each other, so it reduces to 1. That leaves me with x plus 3, which was my numerator right here, minus 3. Well, there's nothing happening inside the parentheses right now, so I can drop it. So if you have a plus 3 and a minus 3, that simplifies down to x. So here's the example of starting off with the f function and then plugging in the g function into the x function and then simplifying, and it's simplified down to x. All right, the same thing is going to happen when we do it the other way. Here we start off with the inverse function, or you could think of this as g. We renamed it g. You could call this g right here, but using the inverse function is just as well. So we take the f function and take the f function and plug it into the inverse. So we're doing the opposite. So this is what the inverse function looked like. Here's where the x went. What are we going to plug in? See, this time we're doing it the other way around. We're taking the f function and we're plugging it into the inverse function. It goes right there. So now we have 2x minus 3 plus 3 all divided by 2. Well, plus 3 and minus 3 add together to give you 0. So that just simplifies down to 2x. The 2's divide out. 2 divided by 2 is 1, so you have a coefficient of 1x. It takes a lot of work to prove that two functions are inverses of each other, but that's what it is. So again, we're still going with the idea of switching, because you have to switch what you have to do. The first time you plug one function into the other, then you switch it and you plug the other function into the other one. So remember the idea behind inverse functions. If you see inverse, you think switch.